Hello everyone, welcome to the topic Eulerian video magnification. This is a computational method that acts as a microscope for very small changes in a video. Developed by a research group at MIT in 2012, it reveals very small changes in color, motion, for example, a person's pulse or the breathing of an infant, and making these variations very large enough for a person's eye to see. So let's go into the topic. Before going deeply into the topic, let's answer the question why we require this method. This is because human eye has a very low noise floor, a limit below which we cannot perceive subtle changes in motion or color. This method provides a software support that pulls these signals, like very small signals like pulse, which we cannot see through our naked eye, and makes them visible. Traditional methods use Lagrangian motion estimation, which attempts to find a feature like a corner of a room or a eye or a small button on the shirt and calculates its velocity vector from very each frame to frame. This method is computationally very heavy and expensive, and it struggles to detect motion smaller than a single pixel. So the proposed method, that is EVM, assumes that if an object moves even slightly, the intensity of a pixel at that point, at that moment, will change. By amplifying that intensity, we push the edge, making the motion visible. This method is less complex, highly sensitive, and can amplify motions which are even smaller than 1 pixel. So let's look on how it works. Below is a video which shows infant sleeping. Here, as as the video is playing now, we cannot see the motion of the video like the infant breathing, which is very small variation happening. Now, on the next video, after we performing the with the software support, we can see clearly that the motion is miming. Like we are not expecting a change in the motion in the hand, but also which is not visible in this video, it's visible here. So this method shows that even small variations which are not we are not expecting are also even visible in this method. Now to understand how this works, we look at the mathematical relationship before explaining the process. So here we determine the relationship between the pixel brightness and motion. Here I of x comma t is the intensity of a pixel at position x and time t. If an object moves even as slightly by a distance delta of t, the new intensity is just the original image shifted by that amount. So let's derive this mathematical step by step. So we start by defining a video signal as I of x comma t. So it essentially consists of a static function f of x, which is undergoing a small transitional uh, variation like delta of t over time. The intensity at this point is like the value of the image shifted at a position x comma delta t. Since the motion delta t is very small, we can approximate this function using the first order Taylor series and obtain this expression, which is I of x comma t is approximately equal to f of x plus delta of t, which is a small variation in time, or into the function, which is the gradient del of f of x by del x. So this breaks the function into two parts: the static background fx and the dynamic change, which is the displacement delta of t, this function over the spatial gradient. Now let's apply a temporal bandpass filter. This filter removes the static term, the f of x, because it doesn't change over time. This leaves us with a single function, that is the change in motion. Let's call this bandpass filter b of x comma t. Now comes the function of the Eulerian thing. We multiply this filtered signal by a factor alpha and add it back to the original image. So after grouping the terms here, in this, after grouping the terms, we see that the original static image fx plus a modified motion term, instead of just delta, our motion is now scaled by 1 plus alpha, as we can see here. Finally, we recognize that it's this new expression, which we simply the Taylor expansion for the larger motion, we can collapse it back to the function form, showing that our processed video is effectively the original image, but shifts by a new factor, that is 1 plus alpha into delta of t. This proves that by amplifying the change in brightness, that is the intensity of each pixel, is mathematically equivalent to the amplifying physical motion. Now let's trace the journey of a single video frame as it moves through the EVM pipeline. This process effectively breaks down the video and modifies it, rebuilds it. At the top, we have these Laplacian layers, which look like the ghostly outlines because they contain only the fine edges, as we can see here, which are the high spatial frequencies. At the bottom, this is a Gaussian residual, which comes after actually the Laplacian layer comes after building the Gaussian pyramid. So this is the Gaussian residues, which contain the coarse, blurry shapes and colors. This step separates sharp edges from smooth gradients, allowing us to process them differently. So next is a temporal filtering phase. Here we stop looking at the image as a picture and start treating every pixel as a time series signal. We apply a bandpass filter as we discussed earlier. The graphs you see here represent that filter. For example, if you are looking for a pulse that we are considering as between 1 to 2 hertz, this step removes the static background like the noise and ignores high frequency noise, isolates the only specific motion that we want to see, and adds it, amplifies it, and then adds it back. This way, only the signal which is required is amplified. As we can see here, by multiplying it by a gain factor alpha and then adding it back to the signal. So, in the final step, that is reconstruction, we collapse the pyramid, stacking the layers back to back together and constructing our final video. So as we discussed in the earlier slide as the pipeline, this process consists of mainly three phases, which is the first one is spatial decomposition, second is the temporal filtering, and third one is the process of amplification and reconstruction. So the spatial decomposition mainly consists of this Gaussian pyramid, which is consider this is the first level GL. This is the level GL plus 1. So as you can see, the GL plus 1 layer is more blurrier and a larger in size than the GL level. So, and to create the Laplacian pyramid from Gaussian pyramid, we first consider copying the smallest level as it is and then scaling this same level into the size of the next level by adding a zero padding between each pixels. Then this level is then subtracted from the next level. As we subtract, we get only the high frequency spatial coordinates here, which is the level, which is the thing only we want here. So we get those ghostly outlines here. So then the doubt which comes into our mind, why do we perform this spatial decomposition, is that different motions in our daily life happen at different scales. Hence, we have to perform this spatial decomposition. So let's consider our Gaussian pyramid level GL, which contains both low frequency and the high frequency input that hasn't been well blurred out yet. The next level, GL plus 1, is more blurry and smaller. So considering we make a Gaussian pyramid function, which is 2D Gaussian, which is given here 2D Gaussian kernel. We convolute this function with each pixels, that is v of x comma y comma t, to get and smooth an image s of x comma y comma t. So after getting this, we form the Gaussian pyramid like level wise. Now to build the Laplacian pyramid, we consider the GL layer and then we upscale the next level to the size of the GL so that we can subtract them, getting only the frequencies which we want. So if we subtract the blurry version from the sharper version, we're left with only the details that were lost during the blurring. And this difference is our Laplacian layer. So as we go into the temporal filtering phase, here we treat each pixel as a time series signal. So where this is where the frequency comes in the algorithm. So we look at the single pixel across time and apply a bandpass filter to extract only the changes happening at that specific frequency. So the filters we use is either ideal or Butterworth. So why consider between ideal and Butterworth? Ideal filters uses the fast Fourier transform to perform any frame to frame processing. So this takes much computational power and which is not accessible during a real-time application. But an ideal filter is best for color magnification. Now, why we consider Butterworth? Butterworth with the filters is a type of recursive filter, and the output is based on the current and the previous outputs. This filter is cheap and works in real time as it doesn't have much computational heavy power need required, and it's also good for motion magnification. But this Butterworth filter is less precise than the ideal filter. So, as we said, Butterworth filter, why not use Bessel? We all know both Butterworth and Bessel have a linear phase response, uh, while Bessel having more linear phase response than Butterworth. Why we not use Bessel? So it's not used because Bessel is having more linear, so it's bad at blocking unwanted background noises, which is the main aim of this project. Then why not Chebyshev and elliptic? So as you can see from this figure, Chebyshev is having ripples in the pass band, while elliptic has ripples in the pass and the stop band both. So which aren't actually good in a video. It creates a pulsing in the video which is actually not there, leading to distorted output signals. So for a first order transfer function, we start with the normalized analog Butterworth low pass filter, that is HFS. So here we're starting with this function h of s is equal to 1 by s plus 1. And in this function, we apply the bandpass transformation to get this transfer function. We map that S plane, which is the HFS. We map the S plane by obtaining the substitution from this S value into this function to get the equation or the transfer function here. So after applying the inverse Z transform into this function, we obtain this equation as shown here. This equation can be written the generalized form into this function. Now let's look at each term in this thing. Here x of n is the current frames pixel value. X of n minus 1 is a pixel value from the previous two frames. Y of n minus 1 is a filtered results from the previous two frames. So as we enter the third phase, which is amplification and reconstruction, let's say we want to extract a human pulse, which is around the range of 1 to 2 hertz. So to do this, we move into the core part, which is the amplification. Here we received the filtered signal and we amplify it using this factor alpha, and we add it back to the original image. This original image is formed of different levels, as we saw that Laplacian level is then filtered and amplified and added to this. So we are getting a Laplacian level in the end, and this Laplacian level is then reconstructed to form the original video frame. So let's go into that process. So here we introduce a new gain factor known as alpha. Here you can think of alpha as a volume norm for motion. If alpha is 0, we see the original video, alpha is 50 or 100. We're multiplying that tiny invisible color change by 50 or 100 times. So currently our magnified signal exists in this separate ghostly looking thing, which is present after summing, okay? So in the previous slide told like this, each filtered signal is amplified and added to the original image to produce this thing itself. So here before reconstruction our process it looks similar to a Laplacian layer itself. Now this Laplacian layer, we start from the top of the pyramid, we upsample it, stretching its size to double its size, and we add the, the Laplacian layers together to form the reconstructed video. Now the result is a standard video file, but with one key difference, that is the specific motion that we targeted are now clearly visible, while the rest of the video remains unchanged. By level, all the way down to the original resolution. So let's visualize this amplification vector using this video. So in this video, as you can see here, up signal comes, we multiply it by alpha and then add it back to the original image. So this creates a new pyramid level where the motion signal is now dominant, effectively tricking the eye into seeing a much larger change that actually occurred. So we obtain a new Laplacian layer after summing this original video and the error video. So let's move into the real world application part of this project. Engineers, we have never seen or heard engineers using this, but actually engineers use this to see the resonant frequencies in machinery, specifically in structural engineering, in where consider building a bridge. If a motor is vibrating at frequency that might cause even the bridge to collapse, and you know that if, for example, a group of army is marching on a bridge, if the resonant frequency of the marching equates into the resonance frequency of that bridge, the bridge collapses. So such a thing, no, so such a thing not to happen, we use this EVM. Here we can see the vibration before even a crack even forms. So we can prevent. As you all know, prevention is better than cure. Now, this is often known as a visual microphone, recovering sound or vibration from objects like a bag of chips or a plant leaf by magnifying even the tiniest movement, which is not seen by us, caused by sound waves. I'm listening to all this, you might be wondering that EVM is a powerful tool, magical solution for every video, but its reliance on a very small signal approximation, fixed pixel analysis leads to several significant limitations. Now, since EVM amplifies tiny changes in pixel values, doesn't distinguish between a real or a sensor noise. For example, person taking a photo in low light condition, you all know camera senses produce thermal noise. EVM considers a frequency range and filters it. But if the thermal noise is between these frequencies, it filters this too and amplifies this. So a result image may not be so accurate as we wanted. Second limitation, since EVM is Eulerian, which is known as fixed pixels, cannot handle large global movements. For example, if a person is breathing but also shifting their weight or talking, the large movement leaks into the filter. For example, frequencies of similar range gets into the filter or surpasses the filter and gets amplified more and more, which is a leak in the filter. The third limitation, since EVM relies on the bandpass filter to isolate the signal, if two signals share the same frequency, EVM cannot separate them. Google Colab have tried to implement the EVM program using the TPU runtime. Here I would require a TPU runtime because here I've used the ideal filter which uses more video frames per second. So the usual CPU runtime won't work. This part of the program does the Gaussian pyramid formation. The Laplacian pyramid function here takes the output of the Gaussian pyramid function and forms the Laplacian pyramid. The reconstruction part happens in this part. Here, as you can see, temporal ideal filter, that's the filtering process using fast Fourier transform defined in NumPy. The main program happens in this part. So as you can see, process has been completed successfully. So here we see a normal shift from tracking feature, which is the Lagrangian method, to filtering pixels. Now EVM provides a computationally efficient bridge between digital signal processing and computer vision, allowing us to extract a very vital physiological and structural data without ever touching the object. So to conclude this EVM method successfully bridges image processing and signal processing to reveal the invisible dynamics of our real world.